They plan was to knock me out the top of the game, but I overstand they truth is all lame. I hold cannons that shoot balls of flame right in they fat mouth, then I carve my name.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
The last topic on the review of vector concepts is the cross product. So again, we have two vectors, A and B, and we calculate their cross product to give a third vector, C. So first of all, note that this is different from the dot product where the result was a scalar, that is just a real number, but the result of a cross product of two vectors is a third vector, which of course has magnitude and direction. The magnitude of the vector C is defined as magnitude of A, magnitude of B, and then the sine of the angle between the two vectors, A and B. Or usually we just write it like this, AB sine theta. What about the direction? The direction of vector C is always such that it's perpendicular to both A and B. So in this example on the left, let's say we are on the xy plane, like this. X could be in this direction and y somewhere like here. So A and B are both on the xy plane, which means that in order for the C to be perpendicular to both of these, it must be somewhere in the z direction. It could be up or down, but it's definitely perpendicular to both only if it's along the z-axis. And how do we determine the actual direction of the C? So here we have the rules on the left. So we start by placing those two vectors tail to tail. And then we take our right hand and point our fingers along the first vector, in this case A, and curl the fingers towards the second one, B. And now when you point your thumb up, that will give direction of the C. This is called the right hand rule. So you must use your right hand to curl from A to B. And curling from A to B with your right hand, your thumb ends up pointing up in this case. So C is along the positive z-axis. We can in fact generalize this rule of cross product between the coordinate axes as follows. So we have I and J and K. So I cross J equals K. Also, if we now see what is J times K, so we could curl our right hand fingers from the y-axis towards the z-axis, and we notice that our thumb is pointing to the x-axis. So this is saying J cross K is I, and also K cross I equals J. So let's put those crosses there, like this. This is a handy little rule for determining the simple cross product between the coordinate axes. The reason why I brought this up was that usually when we calculate the cross product, we don't use this simpler formulation as seen here, because this requires the calculation of the angle between the two vectors and also the length. Usually we know the components of the vectors, and then we have a more general way of calculating the cross product, and it goes as follows. First of all, we have our general vectors. A would be ax I hat plus ay j hat plus az k hat. So components in all directions. Same with the vector b. by j hat and b set k hat. What we have here on the left is the actual definition of, or the formal definition of cross product. It can be calculated as a determinant of the following matrix. On the first row, we have the coordinate axis unit vectors I, j, k, and the second row, the corresponding components of the first vector A, and the third one, the components of the third vector B. And all we have to do now is to evaluate this determinant. If you've never done this before, I'll show you how it's done. And the way we develop this determinant, it's noted by these bars around the matrix, is as follows. So we start from I, like this. Okay, so the first element that we are going to get is going to be in the direction of I, so like this. And then we have something in the front. So what do we have in the front? To evaluate that, we block these two, or that column and that row. And now we are left with only these four terms. And then what do we do next? Is we take product as follows. So ay times bz minus by times az. So those two diagonal products. That's the first part. And then in the second phase, we continue in the same direction. So we are calculating something that comes, or that has j unit vector in the front. But now as we go from left to right, we start with plus, like we had here. And what we have to do, in fact, is to switch signs every time we go to the right. So that's going to be minus, and that's going to be plus. So we have to correct this one. That's going to be negative j. And in this case, we are blocking that column and then the top row. So what we are left then is ax times bz and the third one is when that and that have been blocked. So those have been blocked. So we have minus bx times az. And now the third one, we are blocking this column and that row. So we are only left with these four here. And that's going to be k, and in fact positive k, and we have ax times by minus bx times ay. So in general case, we have a vector C that has components in all three directions, x, y, and z. And these are the individual components in that direction. So for example, this would be C in the x direction. This would be C in the y direction. Note that there's a minus sign there. And this would be the C set. A lot of times building the matrix and calculating its determinant is more straightforward than going this way, like I mentioned earlier. And the reason is that a lot of times some of these components are zero, so these terms start dropping out pretty quickly, and you can get the final answer pretty quickly as well. So where is vector cross product needed? It will pop out in the two instances in the mechanics. First one is angular momentum, and the second one is when we're calculating torque. For example, when we are twisting a bolt with a wrench, for example. But it makes more sense to go through those examples once we get to these topics. But with these two expressions, we can evaluate all the cross products that we will be facing when we are dealing with these problems. And also, of course, we need the right-hand rule to get the direction of the vector if we are able to use the simple formulation instead of the general one.
Oh, 56, nigga, shut the fuck up. Fuck that nigga, run that fucking money.
Run that back, man.
What?
I gotta get out, man. You gotta
Run it back? Alright, run it back.